One thing I love about oceans conferences, though, is meeting old friends, getting lots of hugs, and meeting new people. And one of those new people is our next speaker. I've never had the chance until this morning to meet Carol Ann Clayson. She's from the Woods Hole Oceanographic Institute. And she was introduced to me a couple months ago because of a phenomenal speech that she gave at the Offshore Technology Conference in Houston, Texas this past May. It was one of the, it got a roar of ovations, and I understand it. I didn't get to hear it, but I can't wait to hear it now. So Carol, come on up. I know that 100,000 people got to hear it. We aren't that strong, but we can't wait. Thank you.
And so you know, we'll see what we have. So I'm going to talk today a little bit about science, and because that's kind of what I do, and how we would like to connect some of the really big science questions that we are working on with the industry and the other partners, and I'll show a couple of examples. So I hope to have a few things in this talk that are threads that will follow out through the rest of the week. So I'm just going to speak very briefly about something that you all probably know, but I think it's always good to focus on just briefly. And I'm going to talk about the atmospheric engine. And when I talk about I like to use this analogy because some of us just naturally think in this way, but I think it highlights one of the themes that I'm going to have in this talk, which is on air-sea interaction. So first of all, we have the sun, which is the refinery, basically, and the source of the energy that we have. And we have a pipeline as that energy comes through, and it's a little bit of a leaky pipeline, so some of that just bounces right off the clouds and is lost to the system. But much of it makes its way to the ocean, which then warms up. And the ocean is now the fuel tank for the system. And it exchanges a lot of properties. I'm just going to focus here on heat and moisture through turbulent processes. So we've got, one of the great things about studying air-sea interaction is that you have two turbulent fluids with a permeable barrier, and so lots of exciting things happen, and it's very difficult to always get what's going on. So if you can think about those exchanges are really the fuel injectors to the atmospheric engine. And then the fuel itself is that warm, moist air. Right? That's what drives atmospheric circulation, is that change in pressure caused by regions of warm, moist air. And that then drives wind, which is the engine itself of the atmosphere. But as that wind blows across the surface, it exchanges momentum with the ocean surface, which drives waves and currents and mixing within the ocean. So if you think of it in that way, then it's the brakes. Right? So we have the fuel coming in, and we have the brakes. And you really see that quite well defined when you're looking at things like, as Tom just talked about, hurricanes, where you have the input of warm, moist air driving the storm, but you also have a loss of energy because of the momentum exchange with the ocean. And so you have those two competing factors, energy in and the momentum out. So one of the things that we talk about then is understanding if you have certain environmental or atmospheric and oceanic values of, temperatures and humidities and winds, how much of that gets exchanged? How much heat, how much moisture, how much momentum? And I'll show in a few minutes why we still have some questions about some of that, and particularly so under what we call extreme conditions, one of which would be, of course, hurricanes, where it's rather tricky to get the very, very precise turbulent measurements that you need in order to say, are we really doing a good job with the wind estimates telling us how much momentum and so forth. And that turns out to be a quite important thing when you're looking at hurricanes and how much they're going to intensify. Knowing how much momentum is actually being transferred between the ocean and the atmosphere, how much heat is actually being transferred between the ocean and atmosphere, and how much moisture is being transferred between the ocean and the atmosphere. And these are still questions that are rather open in terms of what does that look like, that transfer at those kinds of speeds. And then, as you know, the fuel in the tank is increasing. I show this a lot when I talk to non-scientific organizations. I talk to boards. I talk to companies that are not necessarily atmospheric, oceanic, science-based. And so this is one of the graphs that I show because I think it's so emblematic of the change that we're seeing in our climate. I almost never show the near surface air temperature change because that's kind of small and not very dramatic. But when you start talking about the heating to the ocean, and I point out that the heat in this figure, the heat that's been gained by the atmosphere from 1960 is in that purple. It's that little tiny bit right on the bottom. Then that, the land and the ice also absorb some. But, something like 93% of all the excess heat in the system is absorbed by the ocean. Then that's a large number. You can see we're talking now about zettajoules. And so I talk about the fact that that's, the amount of heat that's being added to the ocean every 3 to 5 seconds is roughly equivalent to a Hiroshima bomb exchange of heat. And we've been doing this for 60 years, right? So it's a lot of heat. People do respond rather well to that. And getting to this current energy transition, if we're really trying to stay below 1.5 degrees, then we are going to have to make some substantial innovations. Our current pathway of acceleration may not be enough to close the gap, and there'll be, in fact, that's Ocean Visions. We'll be talking a little bit about that because even as fast as we're going to try to make that transition, it's quite possible that even if we do have net zero commitments, that we might not be able to stay below that threshold. McKinsey & Company, I loved this quote from theirs, future growth and energy investments could be driven almost entirely by renewables and decarbonization technologies. So I will say that climate scientists are energized to facilitate energy transition, but we don't always know what the pain points are in that transition. So now I'm going to talk a little bit about air-sea interaction itself and some of the science, and then I'll connect this back in a few moments. So air-sea interaction in the 1990s. When you look at sea surface temperature, which is what's on the left, where the warm water is in the red and the cold water is in the blue, and then you look at wind speed, which is on the right, where the light winds are in the blue and the strong winds are in the red. What you see is where the water is warm, the winds are lighter. Okay? And so that just on the very most general sense, when you look at that, what you see is that that's a negative correlation, right? When the wind speeds are high, the sea surface temperature is low and vice versa. And because of that negative correlation, that essentially means that the atmosphere is driving the ocean. Okay, so when you look at the big scales, sort of the atmosphere is driving the ocean. This is just a little bit more of a quantitative way to look at that. So this is the actual correlation coefficient between those two things. And you can see almost everywhere it's blue, and that blue indicates a negative correlation. So again, that's the ocean is just responding to the atmosphere. And so again, through well in the 90s into the 2000s, this was kind of the prevalent view, is that sort of the ocean is basically just responding to the atmosphere. All right, what we've learned in the last 20 years, it's always useful to feel like we have learned some things in the last 20 years. If you look at the bottom left there, that is a picture of two entirely separate data sets. So in the colored is a high-pass filtered surface wind speed. And the contours, so this is now anomalies from the average, right? The contours are completely different sea surface temperature anomalies. I mean, when you look at that, they almost look like you just contoured the wind speed, but that's not. Two entirely different things, sea surface temperature and wind speed. But even more so when you look at it at that scale, what you get is a positive correlation, not a negative correlation. That positive correlation, so if you're looking at down at the 100 to 1,000 kilometer scales, that positive correlation says that actually those smaller variabilities in the sea surface temperature are driving the wind speed anomalies. So in that case, the ocean is driving the atmosphere at these scales. And in fact, if you high-pass filter that data that I showed previously of the globe, and you do the correlation again, notice that we've gone from blue to red in many, many places across the ocean. That is now indicating ocean forcing of the atmosphere, and that happens at sort of frontal scales and mesoscales, so those smaller scales. So much of what air-sea interaction has shifted to in the last 10 to 20 years has been really trying to understand that. And almost all of that understanding is coming from modeling. And we'll talk about why that's true. So I just talked about horizontal scales. I'm going to spend just a couple of minutes thinking about vertical scales. All right? In this case, we're going to look at vertical scales in the ocean itself. We're just looking at the ocean here. And if you look on the left, what you've got on the top there is just a 5-day model simulation of daily warming of the upper ocean under 3 meter per second winds. So every day, you can see that's day, warms up near the surface, extends downward a little bit, cools off at night, warms up during the day, cools off at night. And then if you look in the afternoon temperature profiles, you can see that it kind of warms up similarly over the top part of the ocean. We call that the diurnal mixed layer, so it's kind of mixed, it's kind of got the same temperature as you go down, and that kind of gives you this very neutral profile. At lighter winds, however, you can see again that daily warming up. But now on the bottom right, what I've shown here is just 8 hours of temperature profiles. And now you can see almost a completely different phenomenon, where you don't have this very mixed part of the upper ocean, but now you have almost this exponential profile. And it's very concentrated in the uppermost meter. All right? So there's been a lot of work done on diurnal sea surface temperature variability. Also going to mention that temperature, heat, is not the only thing that affects the upper part of the ocean. Salinity also is a driver of this. And I'll just show a couple of results from an experiment that NASA performed from 2016 to 2017 in the tropical Eastern Pacific under the ITCZ, the Intertropical Convergence Zone, one of the rainiest places on Earth. And it's always fun being on a ship filled with oceanographers, because they would get up in the morning and they would say, we want to see rain today, so we looked at the forecast. And we got the map of where it's going to rain today, so let's move the ship to where it's going to rain. So I had a little conversation, I kept having this conversation about the forecasts aren't really designed to do that for you, especially in the tropics. And we are in the ITCZ. We don't need to chase rain. Like if we just sit here, it will rain on us, I promise. So sometimes I was successful, and other times we did. We were moving the ship to find the rain, and then they'd get there, and they're like, it's not raining. It's quite possibly true, yes. So we did put out a buoy for a little bit more than a year. On the left and the bottom, you can see the net heat flux. So some days with a lot of sun, light winds, other days rainy, and on the right, you can see the wind speed in blue and the precipitation rate in red. So some days with just lots and lots of rain sitting over this buoy. And if you look at now what's happening in the upper part of the ocean, so you can see this is now, again, over multiple days with depth. Colder waters in blue, warmer waters in red. You can see some of that diurnal variability that sort of kicks in and warming the upper part of the ocean. But then you can also see down below in the salinity, where the more saline water is red and the fresh water is in blue, just those huge inserts of fresh water. And they do tend to sit, sometimes very, very near the surface. So why does that matter? So I was playing around with my one of my 1D ocean model version, and I just ran it for 30 days with the data from the buoy. It's not going to look like reality after 30 days. A one-dimensional ocean model is not going to represent reality after 30 days in a place with advection. So that's not what this was designed to do. I just thought it will be interesting to see what happens when I run it with very high resolution, kind of high resolution, and then something more approaching what typically, if you're lucky, more of a weathery type resolution in the upper ocean. So 3 resolutions, 10 centimeter telescoping, 1 meter, 5 meter. And if you look in the top left there, those are the sea surface temperatures from those 3 runs. There's no difference in the input forcing, no difference in the initialization. The only difference is what the resolution of the model is. Okay? And why is that? On the bottom right, now this is a little bit trickier to figure. This is the picnic line, so the constant density, depth, and you can see that the warmest time, when you're running with the highest resolution model, that picnic line gets shallower and stays shallower more often. That's because at that resolution, we're actually capturing that stratification, that intense change in the upper part of the ocean. So when we capture that, when you have a 5-meter resolution, all of the heat goes equally throughout that 5 meters, right? And so it just sort of warms up altogether. But when you have 10-centimeter resolution, you capture how much heat is actually in the upper 10 centimeters, and then the next 10 centimeters, and then the next 10 centimeters, and so you get a much more stable ocean. So when I show this, one of the most common responses that I get that people say is, you can't be liked. No one wants to run a global climate model simulation at 10 centimeters, right? So how much does it matter? So here is now a coupled model, and this is now a 3D, so this is a WRF atmospheric model coupled to an ocean ROMS model. And we don't have the ROMS model yet at 10-centimeter resolution. We have two simulations here. One is the ocean is at 1 meter resolution, and the other, the ocean, is at 5 meters resolution. On the left is 1 meter, on the right is 5 meters. That is the only, there is nothing else different about these simulations. And what you can see when you look at the 1 meter versus the 5 meter, you see that daily warming, and you see how much stronger that is in the 1 meter resolution. I look at this and I think of the ocean breathing, actually, when I look at this, right? And you can just see the bigger depth. Again, this is not with the highest resolution. This is just the difference with this, just between the 1 and the 5 meter. And I'll get to in just a moment, does this matter, though? So the next question is, does it matter to the atmosphere? But you can also see it in the salinity. So, of course, salinity is a little different. What you do see here is you see the little pop-ups of the freshwater pools as it rains on the surface. And again, they're much stronger in the 1 meter resolution versus the 5 meter resolution. Okay, so did that matter? I mean, these are little things, right? Shallow things, little things. You'd like to just ignore them, have them go away. So did it matter to the atmosphere? So what I have here is a picture of a slice. So we've averaged for 10 days, okay, of what's happening with the rain. And now we've got this slice from south to north there. You can see the latitudes on the bottom. And this is now the accumulated precipitation over those 10 days. The blue is the 1 meter ocean resolution model, and the red is the 5 meter ocean resolution model. Again, that's the only difference between these simulations. And what you see is that the peaks of precipitation have actually shifted in the ITCZ, all right, by demonstrable differences, a degree, right, from 10 days. And the only difference, again, being that we're resolving a little bit better what's happening in the upper part of the ocean. So this is obviously something that we're looking at and investigating, because then the next question then becomes, what can we do about this? How much does it matter on if you go out to monthly or seasonal kinds of variability? And then more importantly, what are we going to do in the ocean models so that we don't have to run the ocean models at these very high resolutions? That's really kind of the next step in all of this. So I focused on heat and moisture and a bit on momentum, but of course I've here just added a few of the other things that are going on near the ocean and atmosphere interface, the creation of aerosols by sea salt, exchanges of carbon between the ocean and the atmosphere, exchanges of DMS. So you've got sulfate particles in the atmosphere, you've got Langmuir circulations in the ocean, you have phytoplankton in the ocean, you've got shear here, there, and everywhere, and you've got internal waves, and again, a number of different processes. And all of these combined are things that we really don't have many observations of, particularly all at the same time and all in the same place. And I'll emphasize this with, here I'm showing what we have in terms of direct measurement of the fluxes. Okay? So we can estimate the fluxes by, again, talking about sort of the mean air and surface temperature and humidity and winds, right? But where we actually go out and measure the fluxes on a consistent basis. And so you can see here the locations of those places where we make direct measurements of the fluxes. We had a buoy from OOI. This is a large NSF program, the Ocean Observing Initiative. So for one glorious year, we had a buoy in the Global Southern Ocean Array, and then, budgets got cut, and that buoy went away. We had a couple of years of the Global Argentine Basin Array. That went away also. So now we have the Pioneer and the Erminger, Papa, and the Coastal Endurance Array. So I like to show this figure because I have a lot of folks at Woods Hole who work in Argo, and there's always a conversation about how data poor the upper ocean is. And so sometimes I just take a look at this picture and tell me how many, we just don't have many direct measurements of fluxes on a consistent basis. There definitely have been research programs and so forth that have gone out to make measurements, but again, those are much fewer than you might imagine. What I've done here is show something that's in some ways an even worse picture. If you thought we could get worse than the previous picture, we can. This is now 20 years, as best as I can find, because there's no central repository for this data. This is like I'm, emailing people. I see a paper. I've heard of a program. I email people. What data do you have? What can you get? We do release radiosondes from islands. And usually those islands are big enough that, for the first 100, 200, 300 meters, it's not a marine boundary layer. It's an internal boundary layer caused by the island sitting there. So from here, I've gone strictly to those times and places where it's been released from a ship or from someplace where the interference is probably quite small, even at the lowest levels. And so in 20 years, these are the direct observations that we have of profiles of temperature, humidity in the atmospheric boundary layer over the ocean. And I've been very generous here. You can see a big box in the Western Pacific. So for over 30 days, there were 180 profiles taken somewhere in that box. That was quite glorious. The Indian Ocean had the Dynamo experiment, which was great. Look at all that stuff in there. Sometimes we have, 115 profiles. My favorite is when you start looking in the Southern Ocean or even over the Kuroshio in the North Pacific, and we've got, I actually put it in there. We have over 10 days, we got 17 profiles in that. In 20 years, this is how little data we have, right? And yet, we really do need to improve our modeling in this region. And I work a lot with satellite data. We're working very hard on our global products to make them better. This is now an anomaly plot. So if you took the mean and then you took the difference from the mean of all the different products and said, what does that look like? If you looked at how much water is being evaporated between the ocean and the atmosphere globally over the last, since 1980-ish, here's what all the different products and models and things would show. It's not worth sitting here and dissecting every single one of those. What I hope you take away from this plot is they don't exactly agree. And so much so that, is there more ocean evaporation? Kind of depends on which data set you're looking at. So we still have much room to grow in. And I would say that over the last 5 years, certainly, and a little bit before that, our lack of understanding of the near-surface atmosphere and the upper ocean and how those interact with each other have become a focal point for the science community. And I'll just show you a few examples. The National Academy of Sciences had a boundary layer workshop, right? And, talked about all the measurements that we need. We're desperate for measurements. Profiles of temperature, you'll see this over and over again. Profiles of temperature and humidity and wind speed would be, great. Actual measurements of fluxes in the atmospheric boundary layer would be even better, but, just those profiles. The national academies did a satellite, the decade, it's the second time they've done it. What observations should we be taking over the next decade? What satellites do we need to be putting up? We divided that up into different goals, science questions, and then ranked them. Air-sea interaction and boundary layers were needed for 3 of the 6 key mission goals. The need for this was measured in 7 out of the 13 most important or very important science questions. Half of them talked about the need for improved boundary layer and air-sea interaction. So NASA started up an incubation team, or an incubation project, because we don't have a satellite right now. We don't have the technology ready to do the observations that we need of the boundary layer. And the idea was, let's work on that now so that at the next decadal survey, people can propose, like we've gone far enough that we can actually get a mission for that. So there's an initial PBL incubation study team report that's out. And now what has happened is we are now into a PBL incubation team, so which is a much more open process. I'm the science team leader for that team. That's why I have, that's why it says contact me if you would like to become part of the community. One of the things that we are wanting to do is that the boundary layer community, especially the atmospheric boundary layer community, is very, very scattered. You have 1 or 2 people at, at NASA Goddard. You've got you have a couple people over here. There may be 1 or 2 people who work on it with every type of model. There are people who do, really hardcore turbulence over the land, and they don't ever talk with the satellite people, and then they don't talk with the marine boundary layer people. And so what we are trying to do is to say we need to create a community of people who care about what's happening near the surface, and how are we going to measure it, and how are we going to model it. And we need to have people as part of this team who are also the people who need the data, who use the data, who have, things that rely on improved accuracy of measurements and forecasting. So that's why I said, we're going to have our first science team meeting in the spring, and that's going to be, again, for as many people as would like to come. There's also a large UN Ocean Decade program called Observing Air-Sea Interaction Strategy, and that's at airseaobs.org. Again, how are we going to do a better job of looking at, observing, and modeling the near surface and boundary layer? I mention this because there is a strong effort to try to bring in industry to this, not just industry, the people who make the sensors, but people who use this data. We had a workshop in June titled Air-Sea Observations for a Productive Ocean, and we talked with offshore wind energy, and we had wind experts and those who work in the wind energy come. And again, trying to say, what do you need? What are we working on? It turns out we need the same types of things. We don't always know that we need the same types of things, and there's a lot of expertise that can happen when you put different groups of people into different rooms. There's the Wind Forecast Improvement Project that we're involved in, WFIP. This is 3, because the first 2 were over land. DOE is funding it, and you can see the team up there with NOAA Labs. We've got non-federal, we've got DOE national labs on it, and we have a user advisory board with companies like Mayflower and Ørsted and Vineyard Wind as part of that. So again, trying to move towards bringing science, engineering, technology, industry, government all together. It's located off the south part of Woods Hole, partly because that was easy for us. And secondly, there's a lot of wind lease areas. You can see those are in the colors in the water, all the different companies that have leased the area there. We also have the Air-Sea Interaction Tower, which you can kind of see on the bottom left, which is a tower that was built through the Office of Naval Research to study air-sea interaction. It's the only tower that I know of in the world that was designed specifically for studying air-sea interaction. So we're making use of that. And essentially, what this is creating as we move into the observation phase is when we total up the assets, like a $300 million offshore laboratory. between the things that we already have there, the Air Sea Interaction Tower, the Martha Vineyard Coastal Observatory, the number of LIDAR buoys that are being put out, the Northeast U.S. Shelf long-term ecological research and ships, the OOI Pioneer Array, other buoys that we're putting in, radiosondes that we're launching. We'll have gliders in the water. We have high-frequency radar that's being placed all around the coast, and a barge that we're putting out with a lot of instruments on it. All right, I have just about 2 minutes left, and so with that, I'm going to talk about, let's see if I can, yeah, that'll make it go. This is something that we developed at Woods Hole called the X-Spar, for Expendable Spar Buoy. And what you'll see from this is, you'll see the deployment of this. The original idea was supported by WHOI internal funds, and then in order to make a prototype, we went to Eastman, yes, Eastman Chemical Company, and they funded the work to get a prototype out and tested. There's a whole story there in and of itself, and if you would like to talk with us about that, you can talk about it with me on the WHOI side and David Golden on the Eastman side, who was instrumental in doing this. What you are seeing here is the deployment of a working X-Spar that was funded by the Office of Naval Research. This was put out during COVID. That was a whole story in and of itself during COVID. And what you'll see is eventually the spar buoy will when they release it, all those of us who were working on this were watching the video and saying, just release it, just release it, just release it, because those instruments at the top do not want to be slapped by the waves. There they've released, and that's what it does. One of the things that was serendipitous is that the X-Spar, which is the thing on the right there in yellow, is placed in a place where the eye of Epsilon. So Epsilon was a transitioned storm. It came through. Wind speeds were over 22 meters per second. The X-Spar captured that. It captured the really fine-scale cold front that came through, the shift in the wind direction. The wave height in the second band of extreme winds was over 10 meters. So think of this sitting there, 10 meters, still returning high-resolution turbulence data that we were calculating direct measurements of stress. Okay? And then it drifted into the eye and survived through that and survived a number of other storms as well in that region. WHOI is partnering with, in more formal ways, through something called the Ocean and Climate Innovation Accelerator. Analog devices is a key component of that. But again, it's a way to bring industry and the work that we're doing together. And I'm going to close, I think, with this. This is an Earth Ventures mission that, I don't know how to go back. That's probably just as well. That is for the first time going to would like to put up a satellite to measure everything we need to look at heat and moisture exchange between the ocean and the atmosphere. There has never actually been a satellite mission to do that. Everything that we do is by using other types of instruments, and data comes in at different times and locations and isn't really optimized for that. So, lots of exciting things going on in the air-sea interaction world, and I just want to thank you for letting me come and talk about them today. Oh, okay. I get time for one question, so make it a good one. And now you're all like, oh, I don't know what a good question would be. There we go.
Hi, Carol Ann. I don't have a physics question, but you showed the zeta joule plot of the heat content,
yeah,
say for the upper 300 meters. What is the change in percent, which could impact our ability to go back to where we were, which of course would take centuries? So you had it in absolute units. What's the percentage change over the last 50 years, say something like that?
Oh, that's a really good question. I don't know what the percentage As a total of the total ocean heat
Correct.
content?
The total heat content.
Yeah, that I don't know off the top of my head what that number is. Yeah. That, I do talk about that number in zettajoules. If that heat were in the atmosphere instead of the ocean, the atmosphere would be warmer by more than 60 degrees Fahrenheit. And we probably wouldn't be having the conversations about climate that we're having right now. Okay, so the ocean has helped us by buffering that, but now it's in a place where it affects many other things, including sea level rise, and it's a place where it's going to be coming out for a very long time. So, Ray, I assume you're going to introduce our next speaker. Thank you so much.